we still have one session in this. It's presented by Aleksandar Ichkov, I guess. So he's a researcher at the Institute of Network Systems at RWTH Aachen University. Welcome. So he is going to give a talk on the towards integration of multimodal sensing for FR2 beam management in OAI. I think, okay, is this a presentation? Thank you.
Hello everyone. Given that I am the only thing standing between you and lunch, and we are late, I'll try to keep it short and interesting. First, thanks for the invite from Paolo, ENI partners organizing the special session, as well as Eurocom hosting us and giving the opportunity to showcase our research from our university. So I think the benefits, challenges of FR2 have been well understood thus far within the OAI community, but as well from a commercial deployments. There are already some limited commercial deployments which at the very end showcase some limited performance, but gives us indication of what the real problems are and why millimeter wave hasn't picked up to the full promise that maybe was expected in 5G and FR2. The focus of this work, or at least and our group, is basically providing agile FR2 beam management, and there the problems, of course, consist in terms of the long-lasting beam sweeping procedures, which are mainly RF KPI based. How do you select the beams? If you have, let's say, very large beam code books, like Professor Raymond mentioned 64, we have the same. So if you have 64, then that takes quite a while to actually do the initial access, but as well, how do you use the logic then to do CSIRS-based radio link monitoring? How do you select these? Do you need long-lasting channel measurements, frequent channel measurements, and so on? So what we are trying to do here is basically go a bit beyond the RF-only FR2 beam management and try to leverage non-RF sensor inputs for providing environment awareness. So basically shifting from the reactive FR2 beam management aspect, where we're like kind of losing the link, it's blocked, and then we are trying to react and catch it, but to go more towards proactive beam management, which is environment aware, where this environment awareness is provided by external sensor inputs, and then maybe moving towards the joint communication sensing as a much greater paradigm, because sensing as a service, right? There is a big consensus that will become part of the upcoming 6G standard within the joint communication sensing ICAS paradigm, and we try to use it also to enhance FR2B management. This has been, let's say, explained in many details by the Ericsson and Qualcomm guys, the talk yesterday, the talk today, but basically the goal here is that the network would be able to provide network-assisted mobility through providing environment awareness, where we have sensing capabilities, where we can sense object trajectories, environment 3D maps, and so on. But there, in general, there exists two types of how you can provide sensing as a service. So one, and there the use cases, the requirements are still being explored within the HexaX and HexaX2, the EU flagship project around 6G. And there exists what we call the network-based sensing, when the network tries to leverage the cellular communication as a sensing service. So it can sense and then do whatever it wants, in a sense, with that sensing information. But another aspect, of course, that has been, let's say, explored and researched is what we call the device-based sensing, where through scheduling services, the network can request state information that comes from sensor inputs that are already available at the end consumer devices, right? Our cell phones consist not only from cellular capabilities, but also GPS positioning sensors, different types of sensors that maybe at some point in some use cases, the network will be able to request this state information, get it back, and use it in a more, let's say, smart way to enhance certain things. What we are exploring in this work is basically using this sensor input, so external multimodal sensor inputs such as radars, LiDARs, GPS positioning cameras, to basically enable environment awareness, either through the processing of a single modality, only LiDAR, only radar, only camera vision, and so on, or through fusion of this information to give a more immersive environment awareness for digital twinning. And you might say, AI ML, right, is not the solution to everything, but here, given the large amount of data that we collect from these sensors, huge piles of data, AI ML has shown to be really a good tool, which I will showcase afterwards with some videos of our demonstration. So how do we enable this? In order to enable this, we have built a multimodal experimental platform. So don't be scared by the slide in that regard. So let's try and walk you a little bit through the hardware that we have kind of compiled within this platform. Left-hand side shows the TX, right-hand side shows the RX. They are still transceiver setup, so you could use them either as TX and RX. But what we have integrated is everything's running on a host PC, which runs the sensor integration and the RF part integration. So we have a LiDAR and a camera, which is connected to the host PC. The host PC runs the whole sensor integration, object detection, and so forth. And from the RF perspective, it is connected via the USRP, which we use as a software-defined radio, where we also enable the GPS positioning that already exists from the USRP. But then we use this USRP, or thanks to our friends from NI, X410, which enables us the wideband support, which can go up to 400 megahertz in this case. But also the other cool thing that we have kind of being able to use now with the new X410 is the improved GPIO capability. And here I want to mention, maybe add to what Professor Raymond has showcased previously, that we are integrating a third RF front end that has not been talked about, but I think many of you already have it in the lab, and those are the phase antenna arrays from the Swedish company Sivers Semiconductors. So in this case, in this platform, we also enable multi-band support. So we enable the full FR2 support when we have the FR2-1, which is the 28 gig phase antenna array in this case, and the 60 gigahertz, or what is referred as a FR2-2. And we are running an SPI control for beam switching, TX-RS switching, and everything else on the Sivers directly from the USRP. So it controls the beams, enables us the switching procedures, sweeping procedures, and so forth. So just around the Sivers, so the Sivers is a fully integrated evaluation board, which actually implements the direct frequency up-down conversion, the beamformance, as well as the RF modules, which in this case on the 28 we have an 8x2 phase antenna array, and on the 60 gigahertz we have an 8x4 phase antenna array. So they are still codebook-based analog beamforming at the very end. So how all of this hardware then gets integrated into a platform? So let's try and look at the scheme, and we start from the top, where you could see that each sensor modality is integrated as its own separate function, which runs in a separate Docker container. In this case, we have the LiDAR, the GPS, the camera, everything runs in its separate Docker container, which then feeds information into our ML-based object detection, depending on which modality you want to use. If you want to use a LiDAR-based object detection, which I will showcase our demo, where we have integrated this LiDAR assisted, but also now we have full support for motion camera object detection. So these are mostly use cases that have already been showcased in the automotive driving, the V2X. So each sensor runs its own Docker, then the AI ML object detection also run in a ROS2 Docker container. There we can also enable external sensors, external object detection algorithms, so you can change the algorithm, you can retrain it, change, then validate it on top of that one. And what is important here is the MQTT interface, which actually enables us to then output this object list or detected object list and use it in a smart way in our RF framework, which in this platform currently runs in GNU Radio, where we have the FR2 compliant, in a sense, SPI control for beam management, where we could do full sweeps, we could do multi-stage codebook beam sweep algorithms, so we can test all sorts of different algorithms beyond the very, very, let's say, simple SSB exhaustive beam search. So here's just a small showcase of how these things actually look after you run everything. On the left-hand side, you have the raw LiDAR point cloud data, and on the right-hand side, you could see that between the TX and RX from the RF side, we have a line-of-sight link. and all the object around it, in a sense, showcase the bounding boxes that have been detected by the AI ML, and this object list has been fed to the GNU Radio platform via MQTT messages. And once there is an object which would block the actual RF signal, we do this in a proactive way where we're actually defining a safe zone around the current serving beam pair link, and then we could switch to a backup beam pair link in a proactive way where we don't wait for the link to actually be completely blocked, to be in a completely blocked outage state, but we're actually doing proactively to kind of enable the link to continue to being served. And these backup links, we already know them because we do periodic SSB beam sweeps in that regard, and we keep, let's say, a basis of potential backup beam pair links, which then can also be monitored via CSIRS. However, GNU Radio has its own limitations, and our goal is to basically replace the complete RF framework that we are currently running in GNU Radio and basically enable full OpenAirInterface stack support, where we could actually leverage the FR2 waveform, frame structure, the resource scheduling, and most importantly, we could derive standard compliant performance metrics over the complete protocol stack. So we can really test the sensing potential and capabilities in such a 5GNR compliant, in this case, protocol stack framework. What has been done thus far? So what has been thus far is that we have enabled the SPI control on the sievers, so we can, it's not yet public as a branch, but we can say that that's maybe the third RF front end in that regard that has now been supported, besides the interdigital that has been shown by Eurocom, Professor Raymond, the TMI Tech device that has been shown by Olbismart, TMI Tech, and I, and Fraunhofer HHI. Now we have also the sievers. As I said, I believe many research labs actually have sievers. So that is integrated. The work in progress is basically the MQTT for a real-time data exchange. So we have done this following some work that also did some MQTT interfaces here by Eurocom. But what we have at the moment is basically we have the MQTT broker and publisher that is running in the ML-based object detection, and then you have the MQTT subscribers or the clients, which can run both on the OAI GMB and on the OAI UE. So they're basically subscribing to these MQTT messages, which are just object lists, so list of objects that have been detected by the different modalities. And now comes basically the control, in a sense. Okay, if I have this object list, how I'm going to use it and for what I'm going to use it in a smart way. So what we have showcased, and I'll showcase afterwards on a video, we are using it to enhance the FR2 beam management for environmental awareness. So we want to bring that in OAI as well, but as you saw, the roadmap is still on the way for basically having standard compliant FR2 beam management procedures, and there we're more than open to continue the development effort with our own changes. However, the big goal actually is to establish what has been talked by Paolo, Olbismart, the NI guys, the HHIs, to establish this open source 5GNR compliant SDR platform, which is there to test different algorithms, but not just on the RF data collection side in a sense, but also on the sensing side. Because now what you can do is, besides collecting large-scale RF measurements, FR2, let's say with the beam manager, but you can also collect these sensing data sets, right, which come from different or like 5GNR compliant timings running in a 5GNR compliant open source platform. And then you can showcase things like digital twins, so how we can use this information for immersive physical cyber continuum, like Ericsson showcased, for detailed network planning. So one of the use cases that we have is we are running detailed site-specific ray tracing simulations for millimeter wave, and there we are using LiDAR point cloud data from our own measurement site to basically get the detailed 3D map And then we are feeding this detailed 3D map into our ray tracer, which kind of gives you, of course, quite some accurate modeling of the environment for your own ray tracing simulation. Beyond that, collecting such large-scale sensing and RF data sets enables you to retrain, validate integrated AI ML models. As we know, two of the three AI ML use cases for the 3GPP air interface in release 19 are closely connected to this, right? The AI ML models for the beam management or enhancing the P1, P2, P3 procedures, right? The GMB and the UE side, depending where are you running these AI models, but as well as for positioning. And there, what our goal is also is to use this sensing data to also validate the potential accuracy that joint communication and sensing in a 5G NR compliant would be able to achieve, because you have the ground truth in a sense from a high resolution LiDAR. Can you achieve that kind of accuracy? Can you achieve that kind of things within open source SDR-based 5G NR platform? So before wrapping up, just two videos to showcase that this is working, and we have let's say demonstrated. The first one is a LiDAR-assisted FR2 beam management that we showcased on the 6G platform, which is an annual conference in Germany, collecting all research projects in Germany. The left-hand side, you see the TX setup. The right-hand side is the RX setup. And as a reflector, because we don't have a wrist, we put a mirror. It worked. Everybody was thinking that's some kind of transparent wrist. No, just a regular mirror. And what is important to look at maybe is this TV on the right-hand side from the RX, where you can actually see the live image from the LiDAR, where you would able to see the detected objects that are coming from the LiDAR as bounding boxes around the people. And in particular, at the moment you see this blue line connecting the TX and RX. That means that there is a running line of sight link, and as soon as the link or a person walks in that's a safe zone with potentially to block the link, it will switch to a known backup link. So let's try. I'll try to click. So I see my colleague will walk into the safe zone and then switches from the line of sight blue link, goes to the backup link, the red, and as soon as it walks away, it switches back. And this is based on the object lead detection, which is basically fed to the actual beam manager. And one more video, just so shout out to our friends from the Institute for Automotive Driving, and that is where this ROS integration has also come in handy with us. So we have integrated our beam manager into automotive driving vehicle platform. So basically we are leveraging the sensing capabilities of the vehicle, which are already used for autonomous driving, LiDAR, camera, object detection, and so forth. We're putting on top our RF platform, and we are getting the sensor input and the detected object directly from the vehicle platform. And that you will be able to see it if you look at the video here, that this is the LiDAR output that is coming from our platform, and this is the LiDAR output from the vehicle directly. And you basically the same principle. As soon as you walk in, the backup link changes, and then you walk out, it switches back to the better beam pair link that it knows, leveraging the sensor inputs from the vehicle. So thank you very much.
Thank you for a very interesting presentation.